In this slideshow, I'd like to talk about a few topics related to the beginning of this class. First, I'd like to talk a little bit about systems and what defines systems, what are the working parts of systems. Second, I'd like to just briefly cover how systems is applied to practice, that is teaching math and science. And then I'm going to talk a little bit about Earth systems and how those are broken out into, and then a little bit about modeling, which is both a math and a science standard and applies to our work with Earth as a system. So this introduction is kind of setting the big stage for our look at weather so that we can have a large-scale context in which to understand weather phenomena and how it can apply to our practice. So here are some aspects of systems that I'd like to talk about in the next few slides. So first, definitions of systems. Well, a system has three basic parts, or three basic parts of their definition. One is that systems contain a series of different components or parts. Secondly, these parts are integrated in that they interact and there are interrelationships between the different parts. And third, that between these components or these parts, there is a transfer of matter and energy. So we know a lot of examples of systems. One thing, there are anatomical systems like the digestive system, the skeletal system, the neurological system, etc. In astronomy, we have the solar system, which has parts like planets and meteorites or meteoroids and asteroids and things like that. Ecosystems, here is one representation of an ecosystem which shows producers, consumers, decomposers, and non-living matter and how they're interrelated. And notice here matter and energy are transferred between these parts. And here's a different diagram or model of an ecosystem. And we have mathematical systems like the number system, which consists of these parts and these types of operations and properties, etc. And then human design systems like cars. These are systems which consist of parts, and these parts interact to get us from one place to another. So how are systems applied to our teaching practice? Well, to answer this question, I went to the Common Core state standards and searched for system, and I, of course, came up with the number system. So the math teachers in the group, one of the types of systems you'll be teaching are numbers. So that's pretty clear. And in the next generation science standards for the science people in the crowd, Earth systems is a disciplinary core idea, in this case covered in 5th grade. And if you look at cross-cutting concepts, which is one of the dimensions of the NGSS, systems and systems models are one of those concepts or set of concepts that go across disciplinary boundaries. So systems are pretty important in both math and science disciplines. So we're going to talk specifically about the Earth system, okay? So the Earth system consists of a variety of what we call spheres, okay? So are different components, okay? And there are many ways to break up the Earth system. We're going to break it up into 4 different places. There's the biosphere, which consists of life. We're a part of the biosphere. There's the geosphere, which consists of land and all the landforms and related processes. And there's the hydrosphere, which consists of the water-based part of the Earth system, such as precipitation, surface water, groundwater, etc. And then the area that we're going to be focusing on, the atmosphere, consists of all the gases, including water vapor, as well as the processes that occur there. Now, some systems break out in the biosphere, they break out man's activities, they call it the anthrosphere, and in the hydrosphere, some people break out the ice, glaciers and so forth, and call it the cryosphere. But we're going to stick with these 4 separations. So how does mass get transferred between these different spheres? Well, these are via biogeochemical cycles, such as the water, nitrogen, and carbon cycle, which we're pretty familiar with, I think. And then energy transfer occurs in two different ways. One is we get our energy input from the sun through solar radiation, and then there's also the internal radioactive decay of elements in the earth, which produces many geologic processes. In the Earth system paradigm, if you will, one of the things we look at is the nature of perturbations. Okay, that is, what happens when we perturb or make some sort of change within one of the spheres, and how is that propagated through the rest of the system? And our end product here is what we're going to be doing is looking at building a model of what this looks like. So here is a perturbation, a major wildfire in Yellowstone back in the 90s. Okay, this clearly has impacts on the biosphere, the hydrosphere, and the geosphere as well. Can destroy soil horizons. Here is a volcanic eruption of a volcano in the Kamchatka Peninsula in Russia. And clearly the eruption of this large amount of gas into the atmosphere can have an impact. So there's the geosphere impacting the atmosphere. And then we clearly have an impact on the atmosphere. This is a picture from Shanghai, or maybe it's Beijing, excuse me, Beijing, that shows the intense air pollution in that part of the world. Okay, so these are perturbations in the different parts of the systems, and one of the things we want to do for our work in this week is to track these. So our goal in one of your assignments is to construct a model of how a perturbation impacts all the spheres of the Earth system. So let's take a look at the volcanic eruption as one change which occurs or starts within the geosphere but has impacts across all other spheres. Okay, now connecting this to our practice, specifically about modeling, which has been a big focus in both the Common Core. Common Core State Standards has a high school standard about modeling. In the next generation science standards, one of the fundamental practices of science is developing and using models. Okay, and a little bit about models. Models there are two general types. There are mental models, which is an eternal idea that you have that you construct in your head. You may not share this. It's idiosyncratic, meaning that it's particular to the individual. And then there are conceptual models, which are more well-developed and public. And types of conceptual models include mathematical models like equations, computational models like computer programs or computer models, pictorial models, which are just diagrams that show relationship between parts, and then physical models that are built and tested and refined to be good representations of natural processes. So a useful saying by George Box, who was a statistician, he said, all models are wrong, some are useful. And the take-home message from this is that in our attempts to represent natural phenomena, we can only get so close to what reality is. So there's bound to be something that's amiss from the natural system. And what we're really looking for are models that are as close as we can get to our observations and our current understanding of the natural world. So here are some characteristics of models to remember. For one thing, models are representations of the real world. They are attempt to connect observations with ideas. They are necessarily simplifications because it's very hard to model or to produce a model that's an exact replica. They have certain boundary conditions. That is, you have to define what the starting and ending conditions the model has in order to construct something that can actually be run. They are predictive, okay? They are testable, and they are revisable. Okay? so these are some of the characteristics of models. So let's look at an example of a conceptual model. In this case, it's just a series of statements about how this volcanic eruption impacts the Earth system. Okay, so the volcanic eruption, the geosphere, impacts the atmosphere by injecting large amounts of fragments and gases into the atmosphere. And the fragments or the gases can change the local composition of the atmosphere, and the fragments, which may have a long lifetime in the atmosphere, may actually affect incoming solar radiation. They may influence the amount coming to the surface and therefore create a cooling. So that is the impact between the geosphere and the atmosphere. Now, in this eruption, the geosphere also influences or impacts the biosphere by destroying local ecosystems. So there is your geosphere to biosphere. The geosphere also impacts the hydrosphere. Mud flows, such as a thing called lahars, can clog river systems and change the courses of rivers. So this is a very simple narrative model, if you will, of how a volcanic eruption that impact is propagated through different parts of the Earth system. So one of your assignments in this week is assignment Exploring Earth Investigations, How Are Earth Spheres Interacting? And what I've asked you to do is, after completing the investigation, construct a model that illustrates how the atmosphere is impacted by changes in the three Earth spheres: geosphere, biosphere, and hydrosphere. This should be pictorial models, and you can provide this as a PowerPoint slide or draw your model, scan it, and submit the scanned version. And this satisfies our learning outcome number 4. Okay, so this is your goal, is after going through this investigation online to come up with some ideas about how the atmosphere, because that's what we're studying, is impacted by events within the geosphere, biosphere, and hydrosphere. So here's of what I did. I'm not a great artist, but I did the best I could. So here is the volcanic eruption, okay, with clouds of gas and these pyroclastic flows going down the side of the slope. And here is a green glacier that sits at the top of the volcano. So here is my model. This is a pictorial model of that process. So the gases and particulate matter influx into the atmosphere. So this is a geosphere to atmosphere impact. I've added to this that solar radiation is reflected by particulates, that's indicated by these bouncing arrows, which results in a cooling. Another impact is this pyroclastic flow flowing down. They can damage the local ecosystem. So that's the geosphere to biosphere interaction. And then the glacial melting producing a mud flow called lahars can infiltrate river systems. That's the geosphere to the hydrosphere. Now I've added one other interaction, and that is the particulate interaction here, which produces a cooling, can also impact the biosphere. So this is a secondary feedback into the system. Now the beauty of models, using these in your classroom, if you're a science teacher, is that now you can go through an activity and have students test these ideas by looking for examples of whether this idea is correct, especially the solar radiation. And therefore the model becomes testable, and if they find new information, they can revise it or they can add to it. So it's pretty powerful. Okay, so here are the image credits. I'm trying to be better about indicating image credits. I hope this presentation helps. Please let me know if you have any questions. Thanks.